Our next speaker, it's really exciting to have Dr. John Donovan here to talk to us. He's the former director of the microanalytical facility at CamCore, which is at the University of Oregon. And he is the president of the Probe Software Incorporated, which is software for running probes, which we've heard a little bit about in the breaks here. He's been an active contributor in the field of microanalysis for 36 years, and his publications focus on the development and optimization of quantitative wavelength dispersive X-ray spectrometry. Today, he's going to talk about how to test and correct for systematic errors in EPMA, which is obviously a super important topic. So I'm going to stop sharing my screen, and if John, can you share your? Oh, I've lost it. Right. Sweet.
Yeah. Do you see it?
Yep, it's not in for a second.
It works.
Oh, perfect. Yep, it's
Fine.
full screen.
Okay.
So yeah, take it away, John.
And Eric, you can call me Mr. Donovan.
Mr. Donovan.
All right. Thank you. Okay, so I'm going to run through these slides fairly quickly, some of the slides fairly quickly, because I think it's just better if they are just read afterwards as a PDF. And Jonas is going to get a PDF of this talk, and I'll put a PDF also on the EPMA user forum. And today I'm just going to do a presentation. Tomorrow I will do a presentation with a lot of demonstration in the software of how you actually do the various light element corrections. But today I'm going to talk about errors in general. When I get done with this kind of talk, people are convinced that you can't do EPMA at all, but that's not true. You can do EPMA. You can just do it better if you think about where your sources of error are, as many of the speakers have discussed. Okay, so this is kind of just a general flow of all the different corrections that we do in our analyses. The microprobe basically generates a K ratio, and that's just the normalized intensity of the unknown to the standard and corrected for everything we can think of. And so this is everything we do after that measurement is in software, and that's why it's important to get the software right. Okay, so we have lots of problems in EPMA. Can I get rid of this thing here? I don't know if I can get rid of the, maybe you don't see it.
We don't see it, so the slide looks great for us. But
okay, great. Okay, so first problem. We need better standards, and this has been mentioned already today, and I just really want to emphasize that point. And, you know, the dead time corrections we've been using since, you know, for probably almost 100 years, basically don't correct for nonlinear effects. And now that we're getting up into hundreds of thousands of counts per second, then we need to do a more advanced dead time correction. We need a better physics-based correction for the backscatter loss correction, which is not mass-based because it's all electrodynamics all the way down. And we need better modeling for the backgrounds for trace elements to support curved backgrounds, complex backgrounds. And we need K-ratio consensus. First of all, does the different spectrometers on my instrument, do they agree with each other? And if they do agree with each other, do they agree with other instruments in other laboratories? And the K-ratio consensus project, which is Nicholas Ritchie has started, will answer that question, because science is about consensus. And we need to think about the way we've been tuning PHAs. With these high count rates, we need to kind of maybe modify the approach. I mentioned that a little bit in the break. And we need to use quantitative interference corrections with zero blanks for accurate trace element determinations. Can you measure zero? We always test with the analytical total if we can measure 100%, but we need to test zero as well. The problem with standards is pretty well laid out in this figure from a recent paper published last year. And it's basically the conclusion of this paper is that every lab produces statistically significantly different results from each other. That is not a good sign in science. We should all be getting the same answer within statistics, but we don't. And why is that? And one reason, there's lots of reasons, but one reason is that we're using different standards that are actually not what we think they are. And so you can see in this plot of iron versus magnesium, and then the aluminum versus sodium here, you know, whoops, let me go back. you can see the labs here that have been revealed, and then this is without the labels, but it's for the other elements there, and that needs to be considered. There's a problem in our field, and we need to fix it. We need global standards, basically. So, and it's worse than that. It's worse than that. Here's an example of the abuse of standards. Even if this was a perfect standard, this would be abuse, statistical abuse of science. So we have somebody analyzing nickel and using San Carlos olivine as the nickel standard. Well, what's wrong with that? Well, the nickel concentration is, 3,000 ppm. It's a tiny amount, and so this is going to produce problems statistically, right? And this is not, if you examine the detection limit equations, you will see that you want to have a standard which is the highest concentration of the element. And the effect of the matrix correction on that trace element is negligible. I will proceed here. So, well, just to explain this. So the statistics is that your errors add in quadrature. And so if you have a concentration in your primary standard, which is low, you're going to create more uncertainty in your measurement. So that's a really bad idea. And second of all, this nickel concentration isn't well constrained in the San Carlos olivine. It's all over the place. So this is a terrible standard. This is the last standard you should use. In fact, you should just not do an analysis if this is your nickel standard in olivine. Use a pure nickel or even or nickel oxide primary standard. That's what you want. What's important for this measurement is the background. Okay, I'll explain. So here's a plot of intensity versus concentration, and you see that we have some non-zero level, which is our background, and at 100% we have some other intensity. And this is a typical kind of absorption curve that we would get from normal matrix effects, okay? If we have a fluorescence dominating, we would get this sort of a curve, okay? That's all it is. And think of it this way. Our primary standard, the correction for our primary standard, the matrix effect, is a multiplicative correction. So we multiply it, okay? Now, on the other hand, the background correction is a subtractive correction, okay? We're just doing simple subtraction. So one is multiplication and one is subtractive, and that has very important differences in the way we treat our data. Okay, what it means is that for major elements, the dominant effects is our standard composition, matrix correction, and the dead time correction. Those are the things that affect the measurement of a major element the most, okay? On the other hand, for trace elements, the dominant effects are background interferences. Okay, let's look at that more closely. So if we have an error in our matrix correction, our standard, or our dead time, a 2% error, accuracy error at 100% yields a 2% absolute error. But a 2% relative error at 100 ppm means a 2 ppm error for trace elements. So the matrix correction is essentially a non-entity for trace elements, okay? And obviously it's zero, okay? So for the major element accuracy, use at least a roughly, or whatever, depends on the situation. You might need a matrix match secondary standard, or at least a little bit matrix match. Use, SiO2 for silicon, or Mg2 SiO4, or something like that. For trace elements, it's very different. For trace elements, the dominant effects are background interferences, and that effect is a subtractive effect. So it stays constant over the entire range of concentration, okay? So that means that if you have a 100 ppm absolute accuracy error at 100 ppm, that's 100% error. That's a terrible analysis. But that same 100 ppm error at 100% is insignificant. It has no effect. So the background doesn't matter for major elements, okay? So we check, and we can check this accuracy using a zero blank with at least a roughly matrix matched synthetic material. It depends on whether the artifact that is causing the background problem, is that in the sample due to an absorption edge, for example, or is it in the detector, say an argon absorption edge? Okay, so best practices. We want to ideally have synthetic homogeneous minerals, pure metals, whatever, if we're doing alloys, whatever. The modern matrix corrections are working really well. Use a primary standard with the highest concentration that you expect to measure. Don't extrapolate. And that's true for both major elements and traces. For checking accuracy, use a secondary standard. And of course, look at your totals and make sure you include all the unanalyzed elements, water, hydroxyl, ferric oxygen. For major element accuracy, what matters is the standard composition, the matrix correction, and the dead time correction. Just remember that. For trace elements, it's a little different. You want to use a high concentration, again, synthetic mineral containing the element. Matrix correction doesn't matter. Remember, the background correction does. Checking accuracy, use a high purity secondary standard with a 0 level. Check 0. 0 is something we can know. And if we do know 0, then we can check it. Don't use dope standards. Those are for dopes. Haha. All right. So for example, for measuring titanium in quartz, we use a synthetic TiO2, and we check the accuracy using a synthetic SiO2. And then also check for secondary boundary fluorescence corrections. I'll mention this later, but in the talk, but there's a free software, CalcSAF standard, and you use the standard software to model the boundary fluorescence using the EPMA Monte Carlo simulation code, and you can know right away that you might have a problem if you get too close to a boundary. That is when you're measuring a trace element next to a grain, the boundary of a grain that has a high concentration of that element. Due to secondary fluorescence, we can actually excite that element depending on the exact physics situation, and we can obtain an artifact of that element, even if the electrons don't even leak into that other phase. Okay, so what matters in trace elements is background and spectral interference. Okay, so this is a problem. Standards have been a problem since the beginning of science, and we are still in this situation in microanalysis. We don't have global standards. It's like pre-metric days. We're not all agreeing on the length of the king's foot. We need to start using a standard that is used by every lab in the world. Okay, this is what we need to work on. And this is what's causing, we think, a lot of the problem we're seeing where these different labs report statistically different results on the same materials. This is intolerable. It's a scientific scandal. So we need to do this. And there's problems with known standards, minerals, that we get tiny amounts of them that contain inclusions, that have a range of composition, that are, all over the place. And these are not standards. I'm sorry. They were at the time that they came up with what the Smithsonian did was fabulous. It was amazing. And they still can have some uses, but you have to use them with knowledge that they are not perfect. Okay. And even commercially based materials can be very problematic. Here's an example of a pure rhodium that was sold that had almost 3% of iron in it. It was not reported. These are, and some people are selling standards that are just normalized EDS analyses. That's not a standard. Okay, so it's a global scientific scandal. Okay, I'm just gonna. So let's do this. Let's go on to the FigMass site. Sign up, join it, and say that you will help create a global standards. If we had a kilogram of each material, whatever it was, synthetic mineral, that could be distributed to every lab, we'd have enough material for generations of microanalysis, and then our microanalysis would be on a sound scientific basis. And we got a lot of these materials already. You can buy them off the shelf. They do need to be characterized. And some minerals may need to be synthesized by academics. Can we make them in sufficient quantities? I think so. I think we just have to make the effort. NSF is not going to fund this, but maybe NIST will help, or different microanalysis societies around the world. We have money. The MAS Society has a good fat bank account, which they've invested in the stock market for some reason I don't understand. But anyway, we can spend some of that money and get these materials and characterize them and distribute them. This is something that we should all be working on. Okay. And some of these materials may already exist in cabinets and shelves and storerooms at national labs and other places like that, where these things were grown in the 60s or 70s or 80s or 90s. So, look for them things. We need to find these synthesized materials. Okay, and by the way, these materials can be extremely useful for all, not just as primary standards, okay? Obviously, they can be used as secondary standards. They can be used, if they're high purity, they can be used as blanks, okay? 5 or 6 nines is all we need for the microprobe. and consider this: these end member synthetics, Mg2SiO4, Fe2SiO4, CaMgSiO3, whatever these minerals are, synthetic minerals are, these are going to test our matrix corrections. Okay, when I've done these tests, the matrix corrections work great, but there are always cases where there's something that we didn't know shows up, and this is the way we discover it. So having these high accuracy synthetic materials is going to be great for testing our matrix corrections. It's going to be great for testing our dead time calibrations, our picoamp meter linearity, and the effective takeoff angle on our microprobe or stage tilt on the SEM. This is great. We want to push the instrument and see where it fails, and then we will know the limits of our instrument. And these synthetic materials, by the way, high purity Mg2SiO4 will always be Mg2SiO4. It can be reproduced in the future. It's not like a one-off. It's like a glass that we can never reproduce again. But these synthetic minerals can be reproduced. Okay, so again, I'm just going to summarize here on the best practices for major element analysis. Okay, you can read this in your spare time. And this is just an example of a typical kind of a secondary standard I run. This is the NIST K412 glass, and you can see here that we give the average. Here's our 4 data points that we've averaged on that secondary standard. Here's the average of the analysis. Here's the published value from what we believe to be the composition of this glass, and here's a percent variance. You might say, oh my gosh, 10% error, but if you'll notice, the difference, the algebraic difference here is 50 ppm, which is actually less than our standard deviation. So this is an acceptable analysis. On our silicon, we're within 0.2%. Okay, so again, you now have an immediate evaluation of the accuracy of your setup and your tuning on your instrument. And so this is what you want to know. This is what we need to know if we're not flying blind. And the numbers here are the standards, the primary standards that we use. So in the case of the silicon, we use another the K411 glass here. Let's see, the aluminum here, 215. That's the USGS synthetic glass, basaltic glass. So these are all pretty good numbers. We're within basically 2% for everything except the traces, and those are within the standard deviation of the analysis. Okay. I use the NIST glasses for silicon analysis as well. They work great. And here again is that figure from the first slide. And I just point out that some of these corrections that we do to the data are a one-time correction. We do the correction to the data and then we drop it into the iterative loops here. But some of the corrections that we do, like the MAN background correction, the quantitative interference correction, right here, you see that. That is an internal iteration loop that gets recalculated for every new matrix correction iteration. So it's a double iteration loop. It's an iteration loop here, then it's an iteration loop here. And this is what allows the interference correction to be completely quantitative. And that applies equally well to other types of corrections involving unanalyzed elements. Okay, that's what specified element means down here. That's for elements that are not analyzed. Okay. And this should apply to both our analytical points and our pixels in our maps. We need to do exactly the same procedure. Whatever this procedure is, we need to do this for our map pixels too. So here's a map from Annette, and this is a raw oxygen map. And if we gaze at this map, because we're map viewing, like moon viewing, we would come to some conclusions about where the oxygen is in this iron titanium oxide. And we would be wrong, because if we quantify that map, we get a very different story. So the point is that seeing is not believing if you're not being quantitative. All right. So we need to correct all these pixels for the background, the dead time, the matrix, and the interferences involved. And as I will show you, even for volatile ion migration effects as well. And then there's, of course, the errors due to unanalyzed elements. This can happen all kinds of ways. Excess oxygen, when ferric iron is present, needs to be included. Water, hydroxyl in both minerals and glasses. These can be corrected for now using charge balance in PFE, which is really cool. There's a paper that just came out on that. This is an example of not including water in a glass analysis when comparing FTIR to microprobe. And the gray symbols are without water in the matrix correction, and the black symbols are water in the matrix correction. So as you can see, you're going to underestimate you're going to overestimate the amount of water by microprobe if you do not include water in matrix correction. And that's because, who would have thunk, water absorbs silicon K alpha X-rays, and it absorbs all X-rays, but silicon being the dominant element in a rhyolite glass, you have to account for that. Okay, and then of course carbon and carbonates and all those things. Here's an example of where John Fresnel, I think, did this, where he did calculated oxygen by stoichiometry, and then he actually measured oxygen down here, as you can see, and you can see the errors in all the elements are like 3%, 2%, 3%. So fluorine is especially affected. Like, so for example, if you have measuring halogens and you calculate oxygen by stoichiometry, you're going to overestimate the amount of oxygen. There's a procedure in Deer-Howey and Zusman where you can subtract that out, but it needs to be subtracted out in the matrix correction because that excess oxygen heavily absorbs fluorine K alpha. And so your fluorine K alpha, your fluorine analyses will be off by around 10, 15% in like fluorphlogophytes and fluorapatites. Okay, beam sensitivity. We've been talking a little bit today about and Annette talked about it yesterday about the sensitivity of some materials to the electron beam. Here's a very beam sensitive glass. This is a synthetic NIST glass that was, I think, used to look at storing radioactive waste. And so it's a very high sodium glass. And as you can see, and this is a log scale, by the way. So this is a log trend here. This is an extreme situation. You probably won't ever see this in a mineral or even a normal natural glass. But it can be corrected for. We can extrapolate back to 0 time. And here's a case for silicon K alpha where we actually have the opposite effect. So as the sodium ions are migrating down deeper into the sample because of this negative subsurface charge to the electrons coming to rest at depth, the silicon K alpha emissions are actually less absorbed. And so you get high intensity increasing over time for silicon. So both of these effects, and of course potassium and any other elements, need to be corrected for as well. These are the different corrections that we can perform in ProFeed. You don't want to overcorrect. You don't want to fit it any more than you need to. So almost all situations will just be the log linear extrapolation. That's a straight line in log space, and it's a very simple correction. And it's done once at the beginning of the analysis. Sensitive materials, you may need what I call the hyper-exponential correction. It's basically a quadratic term fit in log space. And then for the extreme, like synthetic glasses, that high sodium glasses, you do need the double exponential. And that's it right there. And Annette has a paper in preparation, which she'll love to hear me say on all this. All right. So, we can lower the current and we can defocus the beam, but we can also just, and sometimes we can't, maybe we need better statistics. Maybe we have a very small melt inclusion. These TDI corrections can be performed not after the fact in Excel, because then now your composition has changed, so your matrix correction needs to change. It needs to be performed with the matrix correction. Iteratively, that's a mistake. It just needs to be performed once. Okay. Yeah. All right. And as Annette mentioned, she thinks that almost any element under the right conditions will show ion migration volatilization effects. And I think she's correct. This is a figure from her paper she's working on. This is showing trace chromium in lawsonite and phengite. Lawsonite, as you may know, is a hydrous mineral. Basically, it's basically an anorthite with water stuck in the middle of the unit cell. And phengite, that's a sheet silicate. And she sees these TDI effects even for trace elements. Okay, and so here's the thing. Here's an example of where we're doing a quantitative map, okay, of a melt inclusion. in quartz. And there's a couple of things you'll notice here. One thing that I found fascinating is that you see that kind of grid pattern here in the sodium, and you can see it a little bit in the potassium here. That is an artifact of this chart as ion migration in the sample. And what we think is happening, because the beam is not stepping across the sample, the beam is smoothly going across the sample. You know, it's continuously moving. So what's happening here, and I talked to Ben Hansen at Corning Glass, who was one of the people who developed the Gorilla Glass that's in all our cell phones, and that's a very high alkali rich glass, which makes it shatter resistant. He says that what this is caused by is that you've got this moving beam, and then you're dragging along the subsurface electron charge. So I should say you've got this moving subsurface electron charge that is dragging this sack of sodium and potassium ions. And every once in a while, that bag that envelope of ions gets too big, and it just drops off and drops off. And it's an amazingly regular process. But it doesn't matter if it's irregular, we can correct for it. So here's the correction without TDI. Okay, and how do we do TDI on maps? We do multiple frames. We acquire, instead of doing one long map, we do a number of short maps, okay? And the software is designed to automatically take each pixel and extrapolate it back to 0 time. So we get a perfect correction for every pixel in the map, for not only the matrix and background and everything else, but also for the TDI effects, which stands for time-dependent intensity, if I didn't explain that. So what does it look like? Okay, and so we're getting here roughly about 1.8 greenish blue, so somewhere around here is the concentration of the glass in this thing, we think. But when we apply the TDI correction, now we can see that the composition is actually around 3.5%. So that's no small error. So this needs to be quantitatively quantified. And then lo and behold, the artifacts are gone. We have now corrected each pixel for TDI, and we no longer see that stripe pattern. You won't always get that stripe pattern. It happens under certain conditions with pretty high current, but it is amazing to me that we can correct for that. And here's kind of how it happens in real time. So here you can see for the glass, this is the log curve of the intensity over time. You notice we're talking about hours of composition here, and the pixels I'm plotting up here. So this is the first map. I'm sorry, this is the first map here. No, I'm sorry, this is the first map, second map. So this is extrapolating back to 0 time, and we get this correction here for the glass, and here's for the quartz. Of course, there's essentially no sodium in the quartz, but is applied to each pixel. So let's change topics here. Switch, something completely different. We have calibrated our dead time since I started in the field by acquiring a plot of count rate versus beam current. And we look at when we start to, we look at the slope of the line we get, and we try to apply a correction for that. And it assumes a linear model. But this is no longer working. As you can see, even in this older plot here, you can see it going nonlinear here at the end here. So something's going on here. And so let's think about something. We know what a K ratio is. We all know what a K ratio is. It's the intensity of the unknown over the intensity of the standard, right? Corrected for dead time and background. Okay, so again, as I mentioned before, we might not get agreement on multiple spectrometers and even on different labs, but we should. And so what are the causes of this? Well, some of it is the dead time calibrations and PHA adjustments. So I'm going to talk about that. It could also be other types of alignment problems, asymmetrical Bragg diffraction, which is essentially a difference in the effective takeoff angle of each spectrometer. But here's the question. Should this intensity K ratio ideally remain constant as a function of count rate, beam current? So in other words, as you increase your count rate, if you remeasure the same two materials, should you get the same ratio of intensities between them? Think about that. Answer the question in your head, and I'm going to tell you what the answer is. Of course you should. Here's the linear dead time expression that we've all used, and most people still use today. And you'll notice that, and here we plotted K ratio versus beam current. So we're increasing the beam current, which is the count rate on both materials, And we're looking at it, and we can see that it's pretty constant here. It's not too bad, but around 50,000 counts per second, it starts to go haywire, okay? And modern microprobes with large area crystals can easily produce 400,000 counts a second. In fact, I know on some of the Joule instruments, you can get 800,000 counts of silicon on like a silicon oxide or something like that. So this is totally within the wheelhouse of modern instruments, but we're not correcting for it properly. This is the Joule engineer calibrated this spectrometer, and this is from a NETS instrument with 1.32 microseconds, which works again up to about 50,000 counts per second. This is using the linear model that we've all been using since 1937. Let that sink in. You know, that's great, but you know, we can, but it starts to fail. So why is that? And we might say, oh, well, maybe the dead time constant really wasn't calibrated properly. Let's put in, instead of 1.32 seconds, let's put in 1.6 seconds. The problem is that overcorrects the lower intensities, and it still undercorrects the higher intensities. So this is not the answer, okay? What we need to do is we need to go nonlinear. And here's an expression that I found in 1990, that was in the 90s, published actually in a neural net paper, and they have dead time in neural net networks, and they said, okay, let's just take this dead time correction and we're going to add this nonlinear quadratic term. And then when we do that, we apply that to the data, it's flat now out to about 100,000 counts a second. Oh, so we've now doubled the useful range of our instrument. That's pretty cool. Okay. So let's keep going, okay? Because what we realize that is actually that term, that quadratic term, is actually a Taylor series. It's a Maclaurin expansion series, and that can actually be taken out to infinity. I took it out to just 6 places, and tried it, and it worked even better. But then Aurelian Moy pointed out to me that we can do this very simple. We can express that infinite series as a log, and so we did. And this was published last year in microscopy microanalysis. So we're using this. If we use this function, we get the same results at low count rates, but we get much better response. And if we apply it here with the Joule, you know, linear calibration at 1.32, we're slightly overcorrecting. The values at the low, in the low here, those are actually haven't changed, but at the higher count rates, we're overcorrecting a little bit. Okay, and that's because dead time is not a constant, it's a parametric constant, and depends on the form of the expression you're using to fit it. And so if we apply 1.29, just 3/100ths of a microsecond smaller, we get a perfect now our dead time calibration is within our counting statistics. This is what we should be seeing from 10 nanoamps to whatever, 200 nanoamps, 160 nanoamps, whatever. So this means we can get up to about 400,000 counts per second. Above that count rate, things start going haywire again because we're getting saturation of the detector, and the electronic circuits become completely sensitive to the slightest change. So we really, at least with the current electronics, we can't do much better than this. But it's still a 10-fold improvement in our, and this is kind of just a summary. Here's the linear expression calibrated using the Joule engineer value. Here, the blue is using the logarithmic expression with the original dead time constant. And then here we just tweaked that dead time constant a little bit to get a constant K ratio. Constant K ratio just means a zero slope line. All right, and at low count rates, the models all agree. We can also use the same data set to calibrate our picoamp meter. So instead of measuring each of our 2 materials at different beam currents, we take just one primary standard measurement at, say, the lowest beam current, and we analyze all the other beam current measurements on the secondary standard, and we see if our picoamp meter is linear. And the picoamp meter in my Kamika is not linear. It has a big jump, about a percent or two, between the lower range and the upper range. A NETS instrument, on the other hand, was pretty darn linear. That's pretty good. So that's something that we want to check and look for, because if we're measuring samples at low beam current and then we're measuring samples at high beam currents and we're constructing K ratios of them, we're doing analyses, this is a really important correction. Then PHAs, we want to make sure the PHAs are responding linearly, and I have found that people are using the differential mode to try to correct for higher order interferences. It just causes problems. Correct for it quantitatively in the software. And in the PHA, in terms of the hardware alignment, you want to make sure that because of pulse height depression, so here we've got a 10 nanoamp on, I can't remember what material this is, maybe SiO2, I can't remember now. And then this is at 200 nanoamps, and it does shift down a little bit. What we wanted to make sure is that we do not cut off any characteristic X-rays at the baseline voltage. So we want to make sure we have enough gain or bias that we push these curves above the baseline voltage. So no matter what beam current we're using, we're still going to get a linear response from our detector. And by the way, this doesn't matter because in integral mode, those counts, even above the 5 plot here, you won't see them. The instrument does not plot these up, but you're still going to measure all those counts. That's why people thought they could filter higher order pulses. But if we run in integral mode, all those pulses get counted. And there's on the forum, there's a discussion about this showing how you get the same count rates no matter what the amplification of your PHA is. So once we do this, now we can run it. We can measure trace elements and minor elements of the same high beam current, and we can get totals that are quantitative. How much time I got, Erie?
You've got 10 minutes left. That was all I wanted to say, but so you're doing great.
Thank you. Thank you. Okay, and then so we've got we can now do quantitative trace elements and major elements with a high beam current. And now our detection limits for our trace elements, like here's the calcium, you can see 400 ppm. That's a single pixel sensitivity there. So pretty darn good. Okay, so I'm just going to summarize that. And let's see where else now. Okay, this is the backscatter correction we just implemented in the software. There's a paper on this, came out last year. It basically, we're just noting that electron scattering is not a function of atomic weight, it's a function of atomic number. We need to account for the fact that the atom is a spherical atom with but we view it in cross section. So we need to, it's about z to the 2/3, and that ends up being about z to the 0.7 to 0.8 when we actually account for the energy loss. And so here you can see the improvement by using a z-base backscatter correction. So that's another thing we should do. So again, we need to look at these statistics for trace elements. And so this is just saying these, I think. And then this is just a plot of some of the models from this standard program. I don't know if I'll have time to show that, but this is all discussed in this 2018 paper. Here's the software interface, and here's an interesting problem. This is where the intensity actually goes down as you approach a boundary. So this is an iron-nickel alloy here, and we're looking at iron K alpha, and as we approach SiO2, we see a drop-off. That is actually an artifact of self-fluorescence, because the iron-nickel is self-fluorescing, but as you get closer to the boundary of the silicon oxide, you don't get that self-fluorescence anymore. So this is not because your edge is rounded, although it may be, but this is actually a physics artifact that you can observe yourself. This is a real artifact. Okay, and this is discussed on the forum. And I'm just going to do the interference correction because we talked about that a little bit. This is the equation. This is all published in 1992, I think, or 93. And here's without the interference correction. Here's with the interference correction, and I'll draw your attention to the molybdenum here, and I'll zoom in on that by going to this plot here, which I think we sent out as an email. This is pyrite. Here's your chalcopyrite. We would think that there's 1.98% molybdenum in here and 1.2 here, but when we actually apply the interference correction, we actually see there's essentially no molybdenum in there, and in fact, the phase that actually has the molybdenum is this phase right here, which was the low concentration before. So there you go. Yeah, 1993. It's been a while. Complex backgrounds. We can do other things. We can do mean atomic number where we don't even measure the off-peak backgrounds. We model it based on Kramer's law. It works great down to about 200 ppm. We can also, for super sensitive measurements, we can do the multi-point background where we actually measure multiple off-peak backgrounds, and we can fit that iteratively to nonlinear models. And it works. There's a paper by Mike Trasinovic and others that was published that you can read about. And then here's just an example of MAN comparing off-peak. This is the same data. This is off-peak data here. And then which took 20 hours to measure the on-peak and the off-peaks. And then we took the same data and we threw away the off-peak measurements and just modeled it with mean atomic number. You see, we actually get better statistics. Why is that? It's because the MAN background method is dependent on the average Z of the material, which is dominated by the major elements. And the major element statistics are, of course, much better than the continuum statistics. So measuring the off-peaks actually gives you slightly worse statistics. And that is published in 2016. All right, and again, trace accuracy, you can measure zero here, those holes in the continuum that some people have on their PET crystals, and that can be corrected for with the blank correction. Here's the blank correction. I'm just going to zip through this because I think I'm running out of time. But when we did this, we actually got, and this is measuring titanium on all 5 spectrometers. And then, of course, so we have good precision, but they all disagree with each other a little bit in terms of the absolute value, the average here. So what can we do? Well, we can apply the blank correction, which corrects each spectrometer independently. Okay, and here's the equation here, and the blank level can even be non-zero. This was published in 2011. And when we do that, now we can see that we've got, actually, they agree with each other pretty much within statistics now. We can do more. Wait, there's more. And we're getting about, these are the detection limits for each spectrometer, right? 50, 70, 23 ppm. And if we combine them, if we aggregate them, which is just a mouse click on the software, we can now combine them. And now we're getting 3.1 ppm detection limits at 99% confidence t-test by doing all 5 spectrometers as a single giant spectrometer. Okay. And it actually is about 1.4, so it's within a standard deviation. That was with ICP-MS. And then we can even, and this is Aoife McFadden at University of Adelaide. She did these maps, and she basically did multiple spectrometer maps and then combined them with the aggregate feature that you just saw for titanium points, and you get better statistics for that. All right, that's the talk, and this is the summary, and I'm happy to take any questions.
Brilliant. Thanks so much for that, John. So yeah, we've got a few questions here, but also just to say, we've got questions now until the hour, so about 20 minutes. So if people have got questions that are not specifically related to this talk, but other talks or just general ideas, please pop them in the chat and we'll cover those too.
And I've been fast with some of those slides, so I can go back to any slides that somebody has a question about.
Perfect. Awesome. So the first question we've got from Alejandro is regarding secondary reference materials from the Smithsonian. They only provide a single value without errors in their database. To have a better picture, I typically also look at GRM for this. Do you have an alternative? So this is about standards.
Well, like so I mentioned the FIGMAS group in the Microanalysis Society. John Fresnel, Will Knockless. If you go to the Standard Materials Board on the PFE user forum, the Pro Software user forum, there's a topic on synthetic standards, and it discusses this effort, the FIGMAS effort. I think Annette was involved in this too, and she could probably speak to it. But I know that we've gotten some materials. Will is actually in the process of characterizing some commercial materials for traces and homogeneity. And if they pass muster, we will start to distribute them. We want to make a mount for at least the most common geological elements, silicon, iron, calcium, aluminum, sodium, potassium, titanium, whatever, magnesium. So if we could get those distributed globally, I think that would be a huge, because even if you don't even use them yourself as primary standards, you could use them as secondary standards to check your current standards. The problem with Smithsonian standards, they don't have deviations because it was done using wet chemistry. So he got one answer. You can't calculate a deviation on a wet chemistry. So, and like I pointed out in that one of the earlier slides, I mean, there's inclusions in these things, they're homogeneous. The St. Carlos olivine is not a single composition, it's all over the map. So it's just useless. Yes, we all love history. We all love the Gore Mountain garnet and that was collected by ETH, Offenfelder. I mean, that's all great stuff, but I love it as much as anyone. I'm a bit of a rock hound myself, but this is not science. We need to get high purity synthetic oxide and mineral standards and globally distribute them. And there's the link right here on on this slide here. Go there and read about it and contribute. We know that most of these things can be grown. The problem is we just have to get somebody to grow them, whether it's John Hanchar at Memorial University or some company. I mean, most of these materials that are grown synthetically are grown for the semiconductor industry. So let's ride that horse.
Awesome. The second question is more of a about creating a global community. So I guess this is what you've talked about, and having standards and also best practices for working. I think there's a fair, there are journals that are publishing now best practices and methods. So I think there is information out there to kind of look at that. And also, I guess your Pro for EPMA forum is a great place to find that kind of
Yeah, and I'm going to give a
as well.
PDF of this to Jonas, today, and then I'll post it on the forum too, where it stays permanently. It won't disappear after 6 months or whatever the deadline is. But yeah, so there are best practices topics around the globe, and we need to kind of start working together on the worst problems. I think getting global standards is the most important single thing we can do, because the other things are somewhat under our control. We can get better methods, we can get better software, we can do those kind of things. We can do that on our own, but the global standards thing, that requires a community. And so I just appeal to all of you who really want to make a important contribution to the field. Let's work on finding these sources of, whether they're national labs. I know China is growing a lot of these materials, at least in the past, and maybe even today. We've got Russia grew some of these stuff, decades ago. GE, all these places, Union Carbide, they grew these things, and some of them. The saddest story I can tell you is that I know a guy who retired who had giant pools of beautiful synthetic minerals, and he wouldn't give them to us because he said that the microprobe was a waste of time, because he's a laser ablation guy.
So sad.
Yeah,
I
he was a
didn't
bit
realize
of
people had a prejudice against the EPMA.
well, some people do apparently. He was a bit of a
The next question we've got is, in the Pro for EPMA software, how is the relative percentage error calculated, and what is the limit of quantification relative to the detection limit shown in the results?
It's the error is calculated just as you would normally. It's just let's see. Let me get out of this and I'll go back to a slide where it was. Where was that? If you see it, stop me. I think it's this. Yeah, okay. So, oops. So the variance is just the relative difference between the average here and the published value. So, we've got a 50 ppm difference here from 380 ppm, and it should be 430 ppm. That's a 10%. We're 10% low here, and then and that's as simple as it gets. If you're referring to the sensitivity calculations I showed at the end, those are calculated. This detection limit here is a t-test. It's the t-test equation from the Goldstein et al. Book, basically, and it's using students t, of course, and the number of data points you analyze. You can't perform this calculation just like the standard deviation. You have to have more than one data point, and then you want to look at and it looks at the variance here and the students t. Yeah, and everyone knows about the story about students t coming from what was the beer brewing company that did that? Students t. Does anyone know? Anyway, he worked in a brewery, and he was trying to calculate the reproducibility of their product, and so he had to publish under the name student because the company wouldn't let him publish with his name. So that's where it comes from.
Nice. And what is also saying about limit of quantification relative to detection limit? What are you typically? Detection limit is the limit, or?
Well, no. So okay. So that's a good question. So 99% is 3 sigma, okay, And then, this is 95% is 2 sigma, and you can keep going down, So it depends what your criteria. I mean, so in particle physics, they use 6 sigma. I wish we could do that, but we can't. So 3 sigma is pretty much what we do when we're counting photons. In human psychology, it's 2 sigma.
And so if someone has reported a detection limit, is it assumed that it's in EPMA? Do
No,
we
you
assume it's
can't
just
assume. You can't assume.
Cool.
That's why the confidence interval is actually stated here, because you need to know what your sigma assumption is. So always reference that.
Yeah, and I should mention that the different softwares use slightly different calculations. And last year, someone already asked that, and I added to the shared folder a very rough, just like I screenshotted from the various manuals that I have, the statistical calculations that I use in the JOL software, and the Kamika software, and the probe software. Again, often it's in the manuals that you're getting with the software outlined, but it is worthwhile to look at it specifically also if you compare your data against other people's data, if it actually you're talking about the same thing. Are you comparing your data against 3 sigma, 1 sigma? Is it just like an inherently flawed calculation to begin with? So check your manuals, but I did some screenshots also in a document that will be shared with people.
Here's a funny story in that. I don't know if I ever told you the story, but when we first started implementing the TDI correction for hydrous glasses, at Oregon with the various groups there, Paul Wallace and Kathy Cashman, things like that, we had to publish 2 tables in each paper. We had to publish the concentrations not corrected for TDI and corrected for TDI, because no one else was using a TDI correction at that time. So they in order to compare our results to their results, they had to look at the uncorrected data. Of course, now we should all know better that we need to do a time-dependent intensity correction on elements that migrate or are volatile. And I think you did some really good work, Erie, on looking at hydroxyl, right, migrating to the surface, right?
Oh, no, that was Madeline Humphreys. She did
okay.
the work on with the Sims. I sort of used it when I did some of my analysis, but she was the one who measured
Okay,
that.
yeah, so that just goes to show you that, like, yeah, positive ions will go deeper into the sample and therefore lose intensity, but negative ions will go to the surface and get more intensity. So it's worth keeping that in mind, and it's all because it's all electrodynamics all the way down, right?
Yeah, so, like, we love electrons in solids, right? Another comment here is anyone going to EMPG? So that's the experimental petrology, and maybe you can go and spread the good word about creating some standards there. So it's the experimental petrology meeting, I think, for Europe. So if anyone's going there, maybe a good place to try and spread the word on how to get more standards. Thank you, Alejandro. I think,
Sorry, I've been
Annette, you answered a question.
I think that takes them. Well, question rant. I just want to point out that because my experience is usually with these meetings, that specifically to the beginners, they come away with the impression that EPMA as a technique is just this minefield of problems, and there are problems here and there are problems there, and you have to do that, and certain ones are totally outside of your control because you're not the lab manager. And I just want to say that, again, this is an advanced applications, like what are the recent advances topic. We don't talk so much about all the things that work. We're really trying to give some guidance here where there are potential problems. And so if you do something relatively straightforward, most existing softwares handle things like if you do normal Big Ten element characterization in non-beam sensitive minerals, it's working pretty well. But however, there are certain times where there are problems that can occur if you push it towards trace elements, light elements, halogens, like all these things. Every time we push it, and there are sometimes solutions to the problems where we have some way to just mitigate them. by having a wider beam, but that comes at the cost of a loss in spatial resolution or statistics when we lower the current. So a lot of stuff that we talk about is also like how we can have our cake and eat it too, where we have all that and can do it. And I just really want to point out that if you vet your standards properly, it's and you know about their where which ones work and which ones don't in your lab, and which ones you might need to replace with something more appropriate. And if you actually do like some of these K ratio or push the person who can do that, like K ratio tests and dead time tests or something, you can really have a lab, an instrument where you can do very advanced techniques while doing like very straightforward automated analysis. Like I analyze major and minor and trace elements at the same time because my dead time calibration is on point. So there are a lot of advantages, and my usual thing is like this whole matrix match standard to me is like often a scapegoat, where everyone is like, oh, you have to do that, but it's just that you avoid all your instrument problems or standard problems by matrix matching. That's one way how you get
I mean, no,
away from some
and that
problems.
can I interrupt, because I think that's a
Yeah.
really good point. I think that's a very important point you just made. So I think what people have done is, as their instruments have become uncalibrated, and less accurate, and they push them more or push them more, they start getting worse analyses, and they retreat back to the matrix match standards. The problem with the matrix match standards, as you just said, is that you don't know what you don't know. I mean, it looks like you're getting a good analysis, but you have no way of knowing. And so it kind of leads you're now flying blind. And so anything that does go wrong, you won't know, because you've kind of, I mean, back in the day, 30 years ago, when the matrix corrections weren't very good, people did have to kind of use matrix match standards because the matrix corrections just weren't that good. Nowadays, they're really good, but people still have in their mind that they need to do this matrix match. You don't. You really don't. I mean, there are a few very rare cases, black holes in the periodic table, where you might need to, but it's very rare. And as you said, again, 90% of what people might want to do, maybe it's only 80% or 60, but can be done without any of these fancy methods. I just like to focus on what we're doing wrong. If I focus on just what we're doing right, it would be such a boring talk. And
Well, we all agree on that often. And one thing that I would also point out, and that goes into what you showed with the dead times, sometimes we have like really hardware improvements that might then, now we're all like excited about the high intensities that we're getting. But when people not adapt their analytical recipes then to this new hardware, sometimes you actually analyze things worse. I had it where people are like, when you use a focus beam on a tungsten instrument, that's really 1 micron. You can't focus it much more than that. But then I had people who have a field emission now and still use the focus beam settings, and all of a sudden get bad analysis because your beam is actually 20 nanometers. And so the
burning
things
a hole in the sample.
and you use now your high intensity TAPL. I was first like excited by the intensities that I was getting, but now I feel like, oh, I actually want to have a regular size TAP for like major elements because I will run into problems. And so there's things where also staying a little bit up to date and all that, and adapt to your new instrument, and just saying, oh, great, I keep doing it, can be really important. And in the area I see you want to.
I'm going to have to wrap up. I mean, this is really great conversation. But thank you for that. And I just want to have a chance to just thank all our speakers again from today. So we started with Chris Hayward talking about glasses. We then had Stamatis talking about halogen analysis, and finally John talking about errors. And they were really great talks.